Hello. The subject of the presentation is Influence of Programmable Logic Controller Program Structure to Digital Inputs Reaction Time. In the paper there is addressed the problem of influence of PLC program structure to the reaction time of the system in response to changes of input signals. There is presented the research method, followed by research on flat and multi-layer program structures and on the dependence of reaction times in the context of program memory workload. In the research there was used a system comprised of three elements: square waveform generator with relay output as the source of discrete signal, Siemens Sematic S7-1200 series PLC device as a control system, and digital oscilloscope as the measurement and visualization system. There was used ladder diagram, LAD, LD programming language, and the basic program to analyze the influence of filter settings. It was used a single contact controlling the single coil. Operation of the program is to generate the output signal Y when the system recognizes presence of input signal X, and then to reset the output signal when the input is deactivated. Digital inputs of the PLC devices are typically equipped with programmed input filter. Therefore, the preliminary research was to analyze the influence of the input filter settings to the reaction of the system, and there was analyzed the time of reaction of the system output to the changes of input signal. There were measured output digital signal reaction times for positive and negative discrete input signal edges. Measurements were carried out a number of times and the results were averaged. Results are presented in illustrations. It can be observed that response to the negative edge is distinguishably slower than to the positive one. Nevertheless, the relation between input signal and reaction of the system is clear. In case of such a simple program, it could be observed that the overall time of output reaction comprises the filter delay time and about 3 milliseconds time of control system response. Presented figure illustrates a situation where time of input signal changes is comparable to the system reaction time. In this example, the filtering time was set to 12.8 milliseconds and the cycle of changes of the input signal was 40 milliseconds. In this case, the system works near to the safety limit, as under circumstances it can stop to be able to respond properly to changes of input signals, for just one signal, for a number of signals, or for all signals. Following research was to examine the relation between the control system reaction time and the number of simple network components, contacts and coils, in two cases, for flat, single-layer, and multi-layer program structures. The current slide shows various programs with a flat structure. The input filtering time was set to the default 6.4 milliseconds. Results indicate that use of different flat program structures does not make significant difference to the system reaction time, even for a program composed of 64 networks with 8 contacts in each branch. Reaction time did not exceed 9 milliseconds and differences in measurements are negligibly small. The subject of the second part of the research was multi-layer program structures as a natural representation of more complex control problems. Digital control systems of complex nature are constructed with use of functional blocks. In case of the Siemens Sematic platform TIA portal, there can be two types of such structures: FC, functions for operations on external data, and FB, functional blocks, capable to perform operations both on external and embedded data. Functions in most cases are used as data calculation or transformation modules, and function blocks, as equipped with own data blocks, play a role of basic control program elements, in some cases with subcomponents, designed to perform specific control tasks. In the research there was used combination of FB elements. The slide presents examples of multi-layer program structures containing 3 levels nesting of control blocks. It was designed to allow examination of influence of the program's structural complexity on the control system reaction time. The research was carried out for a program blocks comprising 1 to 64 networks, and in each of the networks there was a 8-fold call to FB. In the graph of dependency of response time of PLC output to the change of input signal as function of number of multi-layer networks, it can be observed that reaction time of the system for a single network of 3-layer Containing 24 FB blocks in 3-layer structure, the reaction time is not increased significantly. Nevertheless, the reaction time increases considerably starting from the program structure comprising just 2 such networks and grows up rapidly with the growth of program complexity. In case of the most complicated program structure, including 64 networks, i.e. 192 FB components, the reaction time reaches over 60 milliseconds. Final research area was to examine a relation between program memory load of the PLC device and control system reaction time. The analyzed examples comprise 13 different combinations: 1 single-layer network containing a single contact and 1 coil, 1 single-layer network containing 8 contact in a series and 1 coil, 8 single-layer networks containing a single contact and 1 coil, 64 single-layer networks containing 8 contact in a series and 1 coil, single call-out of 1 FC block, single call-out of 1 FB block, single network with call-out of 8 3-layer blocks, 2 networks with call-out of 8 3-layer program blocks each, 4 networks with call-out of 8 3-layer program blocks each, 8 networks with call-out of 8 3-layer program blocks each, 16 networks with call-out of 8 3-layer program blocks each, 32 networks with call-out of 8 3-layer program blocks each, 64 networks with call-out of 8 3-layer program blocks each. Obtained results do not indicate that there is a simple relation between program memory load and control system reaction time. As the PLC devices are highly sophisticated microprocessor systems and therefore they may unveil some unexpected and device-specific features when executing complex programs. In case of reaction time, it can be observed only a general tendency that can be used to make some inferred conclusions. In first 4 examined examples, program memory load changes from 64 kilobytes to 4 kilobytes and work memory load from 24B to 7 kilobytes. Average reaction time is very similar and can be assumed as constant. In the case of examples 8, 9, 10 and 11, the average reaction times are much worse, and in case of the example 11 there is visible unexpected effect of long reaction time exceeding 20 milliseconds, despite lesser work memory load than in example 4, 7 kilobytes. In this case the reaction time is nearly 3 times longer when compared to the example 4. Similar observations can be made when analyzing the number of simple elements used. When we compare examples 4, flat or single-layer program structure, and 10, multi-layer program structure, it can be observed that in case of the flat program with 576 elements the reaction time is 4 milliseconds, and for multi-layer network containing only 384 elements the reaction time expanded to 8 ms. Obtained results allow to draw a conclusion that it is not possible to estimate the system reaction time basing solely on program memory load or on number of elements used in program networks. During interpreting obtained results, there were considered other relations than can be deduced from the data. It can be observed that there is a relation between number of callouts of function blocks FB and system reaction time. The slide illustrates this relation, forming a graph similar to an exponential function. As a conclusion, it can be stated that the results obtained indicate the complexity of PLC systems results in non-obvious features when analyzing the time of control system reaction to changes of input signals. Therefore, such a time can be unexpectedly long even in case of program with relatively small number of simple basic elements when applied in some specific program structures, e.g., exceeding 60 milliseconds for relatively small program with 192 FB blocks. While use of bigger number of elements can result in shorter reaction times in case of other program structures. Such a conclusion can be useful particularly in case of designing PLC programs for advanced PLC devices such as Siemens Siematic S7 series controllers. It also can be beneficial for engineers designing programs for control systems requiring high time regime, with strict requirements for execution time for particular control tasks. Further research would be aimed to understand better the observed relation between system reaction time and number of FB blocks used, in particular on the impact of the callout structure to increase the reaction time. Thank you for your attention.